Welcome to Work and Power Practice Problems. Number 1, work is required to lift a barbell. How many times more work is required to lift a barbell 3 times as high? So since work is proportional to the height or distance, if we have to raise it 3 times the height, then that's going to take 3 times the amount of work to do that. Number 2, which requires more work to do? Lifting a 10 kilogram box a distance of 2 meters or a 5 kilogram box a distance of 4 meters? Well, let's see. We could actually kind of calculate that out here. But we notice that we have 10 kilograms for 2 meters and then half that mass twice the distance. But we will calculate it out here and see if it is true. So work is force times distance. So 10 kilograms times about 9.8, or let's call it 10, because that would be the force required to lift it, meaning the force of gravity. So for 10 kilogram box, that would be work is force times distance, or about 10 times g, which is about 100 newtons or so, times 2 meters. Is going to be 200 joules of work. We do that same analysis here for the 5 kilogram box. Ooh, I don't know what happened there, everybody. 5 kilograms times G, which is about 10, is 50 times 4. Look at that, 200 joules as well. So sure, if I do half the force for twice the distance, I can do the same amount of work. All right, number 3. Trying to decide, this is to work or not to work, right? That is the question. So for 3A, you're standing, just holding your backpack. Are you doing any work? I would say no, you're not, right? Work is a change in energy. So if you're just standing it, holding it, same potential energy the whole time, no work is going to be done. For B, I wanted to laser point that. For B, you are walking forward carrying a box. Are you doing work on the box? Technically, you are not doing work on the box because you're exerting a force upwards on the box against the force of gravity, which is down. So there is no change in PE of the box. So technically, there is no work being done. You might say, well, aren't I pushing it forward, moving it forward, giving kinetic energy? You are, but you're not opposing a force to do that work. So technically, walking forward, just carrying the box, hey, you're going to get tired, but you're doing no work on it. All right, 3C. You drop your pencil in the hallway. Is work being done on the pencil? Yes, there is work being done on the pencil, not by you, but by the force of gravity, causing it to accelerate and gain kinetic energy on the way down. All right, let's check out number 4 here and our problems. So this is on moving day. You're pushing the box across the floor with a force of 30 newtons for a distance of 2 meters. And we want to know how much work do you do? Well, let's back up for a second and recall that work changes energy. And here, this work is going to give the box kinetic energy, right? As you're pushing, the box has no kinetic energy, and then it will be moving and thus have kinetic energy. So to calculate the work done, that's easy. It's just force times distance, and we're given the force of 30 newtons. And we're going to push that box a distance of 2 meters. So we're doing 60 joules of work. That will also then give the box 60 joules of kinetic energy as well, since work equals the change in kinetic energy. Again, as a result of doing the work, you're increasing the KE of the box. So what is the velocity of the box at 2 meters? We're going to do that right here. You know, if kinetic energy is 1/2 mv squared, and we're doing 60 joules. We have 60 joules of KE, and that box has a mass of 20 kilograms, right? We can solve for V, and let's say 1/2 of 20 is 10, so we divide both sides by 10. So V squared is going to equal 6, and if I do square root of all that, V is going to be equal to, where's the drum roll, everybody? I got to get the calculator out. I think it's like 2.4, right? 6 square root, yeah, 2.45. So 2.45 meters per second, which is about 6 miles per hour or so. How much power was expended to do that? So power is how quickly you do the work. And if we're doing 60 joules of work in 1.5 seconds, let's see how powerful we are. 60 divided by 1.5. Ooh, hold on. 60 divided by 1.5 is, oh, that's not right. Hold on. These calculator probs. It's a struggle today, everybody. 60 divided by 1.5. You probably got it before me. Oh, 40. It's 40 watts. Just like a 40-watt light bulb, right? That would be how much power you would expend. All right, let's keep going, everybody. We got 2 more, 5 and 6 here. Not a lot of room to write this stuff in, but we'll get it. So while out ice skating, you push your friend 60 kilograms across the ice with a force of 80 newtons and give her a velocity of 3 meters per second. So what's her kinetic energy? So let's step back for a moment. It sounds like when you push her, maybe you guys are right here, and you give your friend a push, it sounds like you're doing work on her to change her kinetic energy, right, and get her moving, just like the box problem before. So kinetic energy, that's going to be 1/2 your friend's mass times her velocity squared. So if I do that out, it's 1/2 times 60 kilograms times 3 meters per second squared. So, let's see. 3 squared is 9 times 60. I'm really having struggles with the calculator, people. 9 times 60 times 0.5, and that looks like she's going to be having 270 joules of KE. So how much work did you do? Well, if she has 270 joules of KE now, you will also have done 270 joules of work that gave her that kinetic energy. We want to know how far did you push your friend across the ice? All right. So work is force times distance, correct? So if you did 270 joules of work and by applying a force of 80 newtons, how far did you push her? So 270 there divided by 80 is going to be a distance of about 3.38 meters, right? Because work is force times distance. So if I exert a force of 80 newtons and do 270 joules of work, what was that distance I pushed? There you go, 3.38. For D, it says after you stop pushing, you observe she eventually coasts to a stop, right? That's going to be due to friction, right? Here, the force of friction is going to do that work and cause her to stop for a certain distance, and friction will be doing that work. How much work? I know it doesn't say that, but if she's going to end up having a kinetic energy of 0, friction's going to do the same 270 joules of work to bring her to a stop. All right, number 6. We're doing the staircase run here. 90 kilogram student runs up the stairs, 3 meters in 2.6 seconds. We want to figure out if this student generated 1 horsepower in climbing those stairs. So what's the weight of the student or force of gravity? So when you run up the stairs, you have to apply a force on your body at least equal to your weight to get yourself up the stairs. So that force of gravity on you is just your mass times g, or 9.8. So 90 kilos times 9.8 meters per second squared. So 90 times 9.8. I have 882 newtons will be the force you're going to need to apply to yourself. So the work done then, so if this staircase is 3 meters high above the ground, so that means I have to apply that force for a distance of 3 meters. So 882 newtons over 3 meters of distance. So times 3, I have 2646 joules of work I will be doing. So how much power was expended for this student, right? So power is how quickly the student's doing the work. let's see, so 46 joules of work done in 2.6 seconds. Where's my drum roll? 2.6. Oh, that's 1,017, 18 if I do whole numbers, watts of power. So 1 horsepower, if you remember, is 746 watts. So this is definitely greater than 1. If I divide it out, that looks like it is equivalent roughly to 1.36 horses. All right, thanks everybody.